So another type of synthesis using beta dicarbonyl compounds is the malonic ester synthesis, and this is going to be using a beta diester. And typically you use diethyl malonate. This is going to be a method to synthesize substituted acetic acids. So previously when we saw the acetoacetic ester synthesis, that one was to make substituted methyl ketones. This one is considered making substituted acetic acids because you're going to keep 2 carbons from the malonate structure, and your alpha carbon is going to be the alpha carbon here as well. So here's acetic acid, and here is your substitution. And of course, that substitution will vary depending on what you use your enolate to attack. So in order to get from diethyl malonate to 1, 2, 3, 4, 5, 6 hexanoic acid, we are going to have to add on 4 carbons somehow. And I think we probably know how, right? So we are going to add in ethoxide, because again, we want our base to match our esters, and we're going to use that to make an enolate. So now we have our enolate, we can add in our 4 carbons and a leaving group, and that will give us a substituted diester. Remember to count your carbons here, we're adding on 4. 1, 2, 3, 4. So that our final product is going to end up with 1, 2, 3, 4, 5, 6 once we get rid of this, right? So always do your carbon accounting. So I want to break down the steps that we're about to go through. So our first step is going to be hydrolysis. We are going to hydrolyze those esters to the carboxylic acids. Realistically, we'd probably have to heat this up to get them to hydrolyze, and when we heated them up, it would also decarboxylate, but we're going to put this step by step for a second. And then you heat it up, and you would end up getting rid of one of the carboxylic acids. Doesn't matter which one, you would end up with the same thing no matter what. So this is the malonic ester synthesis, and you can use this in exactly the same way that we used the acetoacetic ester synthesis in the previous chunk of notes. You could use it to react with an alpha halocarboxylic acid. You could add on an acyl group. There are so many things that you could do with this. The only thing you would be changing out is this step here. It all depends on what your electrophile is going to be. So, for example, here's a synthesis. We're going from diethyl malonate to our substituted acetic acid. Notice we've added on an ethyl group and a propyl group. So we're going to have to do 2 different nucleophilic substitutions to get there, just like we did with our previous dialkylation. So add in ethoxide. I'm not going to draw in the formation of the enolate again because that would be the 20th time, I think, in the last hour and a half for me. And it's probably getting repetitive for you as well. So there's our enolate. We can add on either our ethyl group or our propyl group first. It doesn't really matter. I'm going to add on the ethyl group first just because it's smaller and it's going to add less bulk. But if you added on the propyl group first, that wouldn't really be wrong. Add in ethoxide again. We have our ethyl group still. Now we have an enolate. Add in 3 carbons this time. So now we have an ethyl group and a propyl group. And again, in one fell swoop if we want to. We can hydrolyze and decarboxylate to get to our single carboxylic acid. So notice that this whole thing is really repetitive, no matter whether we're doing the acetoacetic ester synthesis or the malonic ester synthesis. These are so similar. Ooh, this one's really cool. So this one, you just have to get a little more creative than you did previously. You have to backtrack again. You have to think about how would I actually make this cyclic structure? So what would have been before this, right? We know that our last step in these syntheses is always to hydrolyze and decarboxylate. So what we would have had before this would be this compound here. Now, what I want you to notice about this is that this carbon is actually part of the ring, which means we did not attack this structure. That's not what we did, because if we attacked bromocyclopentane, our ring would actually be hanging off of our ester. So this is a sidebar. This is not really part of the synthesis. So you'd have your bond, and then you'd have your cyclopentane ring. So that is not what happened here. Instead, we added on 4 carbons somehow, right? And it ended up creating a cyclic structure. Now, what we've seen in the past is that anytime we've created a cyclic structure, it was because we had 2 functional groups on the same compound. So keeping that in mind, same first step. So if anyone found organic chemistry repetitive before, now you really, really feel it. So we want to add on 4 carbons, right? So we're going to have 4 carbons and a leaving group. 1, 2, 3, 4. But we need to have a leaving group on carbon 4 also. And then we're going to have a stepwise addition. So we've added on 1, 2, 3, 4, and here's our bromine. So if we pull off the alpha hydrogen again and create an enolate, we're going to be able to attack this carbon here and kick out the bromine and create our cyclic structure. So there we go. So really not too bad. You just have to use a little bit of creativity, but again, don't get too creative. Don't go like way off and forget all these things that you've done before, right? You add on what you want and a leaving group. In this one, we just had to get creative about the fact that there were 2 leaving groups on the same molecule. And always when you're doing a synthesis, double check yourself. If you had decided to use bromocyclopentane, make sure that you actually think about the mechanism of what happens when you add a nucleophile to this, right? You're going to create a bond to the cyclopentane, and your carbon, that's your nucleophile, would not be part of the cyclopentane. So always, draw out those products as you're thinking through your different options, and that'll help, prevent you from making a silly mistake. So this next topic kind of gets lumped in here. It's not necessarily using esters and ketones anymore. An active hydrogen compound is a catch-all term for when you have a carbon that has 2 electron withdrawing groups on it, and they could be the same or they could be different. That's why we have Z and Z prime, and there are many different options of what these could be. So it could be a ketone, right? That would be like what we've seen before. All those compounds we've been looking at in this chapter so far would be active hydrogen compounds. It could be an aldehyde, it could be an ester, an amide, we haven't done that yet, or a nitrile. It could be a nitro group. Remember this from the aromatic chapter. We haven't seen it very much since then. Or you could have a whole bunch of different sulfur containing options, right? We don't really see these very often, but they do exist, and they are electron withdrawing groups, and any carbon that was next to them or alpha to them would have acidic hydrogens, and therefore you could do very similar chemistry with these. Now notice some of these can be hydrolyzed back to carboxylic acids, but not all of them can. So some of them can be used in the same way that we use the acetoacetic ester, or the way that we just used diethyl malonate. Most of these are going to end up giving you some really interesting products and kind of open up your synthetic possibilities. So ethyl cyanoacetate is a really great starting material. That's this guy right here. So in this problem, I've actually given you a set of reagents, and we're just going to talk through how to approach something like this. So in this first step, we have sodium ethoxide in ethanol. That just means that we're adding in ethoxide. Therefore, ethoxide is going to be interested in pulling off that proton there. So after step 1, we're still going to have our nitrile. Nothing's going to happen to that. Make sure you do not lose the nitrile carbon. So if you struggle with keeping your carbons, you can draw some dots in there. Make sure that you don't lose any. And then we're adding in 2-iodopropane. So what that's going to do is a little SN2 reaction. And now we have our nitrile. And we also have this isopropyl group. And then we're following it up with an aqueous acid workup. Whoops, I did not land in the box. That was supposed to be in the box. And then we could actually repeat the process if we wanted to. We could add on another isopropyl group because we do have another hydrogen. And I'm not going to draw out step 1 and step 2 this time because I think you guys have got it. And that can add on 2 isopropyl groups.